negative gradient. So that tells you how things flow. This vector field here, right? So who's a chemical engineering major? Okay. So quantum chemistry, you're going to do the Schrodinger equation, right? So they put an I in it, right? And then they have this is some energy function, a Hamiltonian. And, did I put U there? I didn't mean that. Psi. For psi is complex values, so this represents a state variable for typically some sort of chemical system. It's going to have a quantum behaviors. But quantum is a crazy word, and people get crazy, like, oh, this is really weird. But you guys have actually dealt with things that are very reminiscent of quantum mechanics, which is the idea that there are discrete modes, right? The idea that you get discrete eigenvalues, right? That is the essence of quantum mechanics. The fact that there's not a continuous spectrum, but a discrete spectrum. The idea that waves on a vibrating string have fixed frequencies to them, right? And they're integer multiples of each other, correct? Okay. That's the essence of quantum mechanics, and when you solve for wave functions, it's exactly what you get. You get discrete frequency waves, and that's, of course, exactly what they show in quantum mechanics. It's exactly the kind of things you get out of black body radiation. In fact, that at high energies, you start seeing one frequency and another, but nothing in between. And it was inexplicable at first until they finally realized it was a solution to standard PE. So if you do mechanical vibrations, of course, you'll probably study things like the beam equation. We haven't done the beam equation in this class, but it's a fourth order PE, where U is now the displacement of a beam. And you get forces both of elastic forces, but also forces that are related to the compression of the beam, right? And that leads to a fourth order PE. Solving those, the Euler beam equation and things related to it, something that a lot of mechanical engineering people may do. So if I think they have a whole class on steel beams, right? Someone told me about this, right? The beam equation. They get a big book that says steel. I've seen it. Right? And I looked into it, and it's all moments of inertia and bending moments and all this stuff, and how various beams, they go through and solve all the PDEs for various profiles of beams, right? So, and then, this is tables and tables and tables, right? But they're all related to analysis of equations like this. Okay? Let's see, what else? But, energy spectral density shows up, of course. So, there's energy spectral density questions on your exam, right? So, but I think there was a request to do more, I don't know, there was a request to do something. What should we do today? Yeah.
Like the heat diffusion kernels and D-Lamberts.
Yes. D'Alemberts, okay, yeah. So, I think that's something that should be on the list. So with D'Alemberts, let's start there, and we'll go back to the heat kernel in a sec, okay? So, D'Alembert, let's write it down. So, it's the wave equation. And it's x on the real line. And you always have a initial position and initial velocity. And the solution is given to you. I'm just going to give it to you. You don't have to find it. Sometimes I've made people doing their homework find the solution via Fourier transform, but it's a bit too much heavy lifting. I thought it better just analyze the solution. So we have So this is the, I should say that's the right going, this is the left going wave. This is the right. Okay, so let's study this.
Just to clarify, is in the parentheses, is that a capital F or a lowercase?
Lowercase.
Okay.
These are all lowercase. You don't have to actually do a Fourier transform of this. This is the result of a bunch of transform methods. We didn't cover it, but here's the solution of it. And so, I think one of the questions that I talked about before was, how do I get just the left or right going wave solution? So again, this is the displacement. F is the displacement, and G is the initial velocity, right? And the idea here is that let's say if I give you an example. One question I can give you is like this. Okay, let's say that I give a kick to this at time 0 and at space 0, at x equals 0. I give a kick to my elastic string. So F, I'll say, is equal to 0, and G is going to be delta of x. Okay. All right. So the question may be, at x equals, let's say, 10. Okay. What time will u of x comma at 10 comma t not be equal to 0? Well, let's find out. Okay, so first of all, f is 0, right? So u of x comma t. One over 2c integral x minus c t x plus c. Now we put that delta function in there. All right, so the delta function has that property that if the domain of integration covers the c equals 0 point, then what's the value of it? Remember? So we'll go b c b f of x and x. That's going to be equal to f at a if a is in bc and 0 else. Okay, and that's on your sheet, right? So is this domain for time that's positive? Is this always going to have? Is this domain always cover C? Or always cover the delta, sorry. What does this domain look like? Everyone looks at this and is like, what's going on? I don't get this. It's an integral, guys. Come on. Where's the domain of integration? Pick an x, right? What are we going to pick? What do we want to pick for x? 10. Plug in 10 there, right? Okay. So where's the domain of integration? There's 10. And that's 10 minus ct. Then 10 plus ct, right? There's 0, right? Okay. When will this finally cover the 0 point? So we need x minus ct equals 0, right? Otherwise, what we say is 10 over c is equal to t. So at 10 over c, at that time, what's the value of u? So what we say is then 0 when t is less than 10 over c, and it's equal to 1 when t is greater than or equal to 10 over c. So if I'm at x equals 10, I'm just looking at the height of my string. It goes like this. Again, this is in the time domain. Yeah?
Isn't it 1 over 2c? This is that term.
Oh, right. So 1 over 2c. And there we go. That's right. You get a swift kick at x equals 0, and it just and that displacement makes it just propagates out. And at x equals 10, after a certain amount of time, eventually that displacement propagates out to that point. But it takes some time to do that. So I might ask you, plot at a particular point in space, plot what the solution looks like in time. Or I may say, at a specific time, tell me the snapshot of what this looks like in space. Should I look at, let's say if C, maybe we'll do another one then here. If C is equal to 1, okay, keep it simple, and T is equal to 2, draw u of x comma 2. Right, so now I'm drawing in space, right? This is a space-time equation, so we're looking at sort of snapshots in time, or profiles in time of a certain point in space, right? So let's do this here. This is our thing. So now we're going to go right? Okay, so when does that domain cover the delta? So this is the C domain, right? And that's 0. And then I have this sliding domain of integration, right? So when this slides along, but when it slides over and hits the 0 point, right, what happens to this thing? It becomes it becomes 1 when 0 is an element of x minus 2, x plus 2, 0 else. Okay. So what x values yield 1? Does x equals 10? No. X equals 3? No.
So 3 negative 3?
So if x equals 2, this becomes a 0, right? That's what we want, right? For not a positive value. Right? And then if x equals negative 2, this slides all the way over to here and then finally leaves. So if anything lower. So another way of writing this is 1 over 2c is equal to 1 when x is an element of negative 2 to 2 and 0 else. So if I were to give this a plot, function looks like this. So at 2 seconds, that's what this string looks like. It looks like, whatever the initial pulse I gave it, time equals 0, it's propagated out to do this. And as it goes further in time, it's going to keep propagating. It's just going to keep doing this, right? And keep going out as time goes forward. Right? So these problems are good. It helps you. What I like about it is it helps you tie it with the map. You actually have to do these integrations and check out these integrations, but it also makes you think in terms of space-time. And that's what I really want you guys to get out of this. Yeah?
Why isn't there like a point discount really zero? It goes to infinity because the energy that was initially applied there. Why isn't that part of the graph?
At zero.
Yeah, because that's where our delta function starts. So it should be like infinite at zero. Because otherwise there's no reason for it to expand.
So notice that the delta function is underneath an integral, always.
Sure.
Okay. So by definition, minus epsilon plus epsilon.
Why doesn't that I just feel like that violates something because it's like we're expanding without losing any of our initial. It's just physically, it doesn't make sense to me why. It makes sense to me at points in time why that would be true. But if we were to look at this graph over a series of time intervals, it seems like you'd be getting more volume. Like as you expand outwards, you're getting increased volume without that energy coming.
All right. So you're thinking in terms of energy. That's a great. Okay. So let's get to another type of problem that was also on the exam. So maybe this is a good tie-in. All right. So how does this relate to energy? Right. So how do we write down energy again? Energy as a function of time. Now this is going to be over the whole real line, right? Because there's over 1/2, right? What do we put here? We put a rho 1/2 mv squared, right? So. Right? And then, so now we have, that's kinetic energy, right? So at this snapshot in time, where is the movement happening in the string? Is the string moving here, or is it staying put? That's never going to move again, right? It's done its movement, right? And down here, it hasn't moved yet. The only point where there's movement is right here and here. Kind of crazy, huh? And if I were to take this derivative, you could think of, and so this is actually true, that the d dt of the heaviside, and this is all in quotes. This is all done what they call this is a weak formulation. These aren't actual functions. These are what they call generalized functionals. That the derivative of a step function is a delta function, right? Right? Because you have zero slope everywhere and then infinite slope at a single point, right? Okay. Yeah.
Does the 1/2, the amplitude, the 1/2 come from the 1/2c?
Yes, that's exactly where it comes from. All right, so for kinetic energy, there's only 2 points where there's motion, right? And the total kind of volume, say, is just these 2 points. That's the only 2 points where there's motion. So, and that's for every time. There's only going to be 2 points, just the 2 wave fronts, right? So that seems to be down there. So I can put the deltas right in there. There's 2 of them, right? And one of them is plus and one of them is minus, right? You see here, there's a negative infinite slope here and a positive infinite slope there, right? Okay. So we'll get to that in a second. Then what do we have here? We have the T, the tension of the string, times ux, quantity squared dx. All right, so ux. So if we want to look at this, we have to look at this as both space and time, which is problematic, right? So we could also look at the spatial derivatives. I mean, what we're looking here is actually spatial derivative. We could think of it as a time derivative too, right? So it's a bit, because this edge is both in the space and time, this is a snapshot, sort of a slice through this solution surface. So what does the solution surface look like, right? Here's X, and there's T, right? It's going to start here at a single point, and then propagate out like this, right? Sort of like that. It's going to be this wedge that just keeps growing, right? And the slope here, this angle, that's of course related to c, the wave speed, right? So if I take a time derivative, I'm taking a directional derivative in that direction, and I take a space derivative, I'm taking a directional derivative in that direction. So either way, I hit that edge. But you see here how I get a delta function twice in space, right? And then I get another delta function here in space, two of them, one for each wave front, the face of the waves, right? And then we have to find a way to, what is a delta functional squared? How we deal with that. It can be dealt with. But the point here is, and I think we'll leave it at this, is that those 2 points are always fixed. They never grow in size. They're always just two discrete points. So I did put a fixed amount of energy in the system. I did put an infinitely strong amount of energy, but it was over a region of space that was infinitesimally small. And I kept the ratio of basically energy per unit of space constant. And that is the definition of the delta functional, the idea that although I have a really extremely violent whack to that string, but it's over a very, very small amount of space. And therefore, the total amount of energy that I put to the system was fixed. So the momentum transfer, the total energy is fixed. Yeah. And this would give you a constant. Some sort of constant. I shouldn't use that constant. Constant C. Yeah.
Would it be improper to say that even if we have any potential energy is also at those boundary points, because our concavity or the slope of the string, like right at x is 0, so there's no potential.
Yeah. Yeah, there's no actual energy potential because the string, the energy comes from its slope, right? So the energy comes from the slope, so you don't actually get anything out of it separate these points in space. Okay? And so the energy is always fixed. Of course, this is why, if you hit, a string with a hammer, the hammer has some width to it, right? Right? And if I hit it with a mallet, of course, the same amount of energy going into it is going to be spread over more space, right? So, kinetic energy of a bullet, because it's sharp and pointy and small, can go right through you. If I go to a slightly bigger round thing, right? The same amount of kinetic energy, it would bounce right off you and you'd be fine, right? And that's why bullets are so terrible, is they have a lot of kinetic energy in a very small package, right? So, okay, so I hope that gives you a better sense of how this works. So yeah, the delta functionals are crazy. I think the best way to think of the delta function is as a limiting process of something that's finite. So again, you're actually giving a pulse of momentum transfer over some finite width, but you're just making that width smaller and smaller and smaller. So what's nice about it is the delta functionals work really well under intervals. They give you really nice, quick answers that would take a lot more work and a lot more detail, finickiness, if I had to do it over any kind of finite width. Yeah. Non-zero width, I should say. Yeah. So other questions? I think there's the theory of distributions, they call it, that uses delta functionals a lot. And it's also essential in what we do. The heat kernel is actually the solution to a delta function pulse. So if I give a pulse of energy at a certain point in a metal rod, the heat kernel is the solution to that tiny pulse. It's the idea of taking a drop. It's also in the diffusion perspective is taking a tiny drop of some sort of diffusing chemical, and putting it in a very large tank of water, and watching it diffuse out. And the idea behind the convolution theorem is that if I had some distribution of chemical and I want to know how it diffuses, I can think of each point in space as being its own little delta functional, and then add up all of those effects from all those little drops of pollution. And that's through that convolution integral. Okay, so those are a few things. So the kind of questions I'm going to give you on the D'Alembert solution are going to be graphical in nature, and they're going to usually allow you to have to I want you to pick through the idea that space and time both play a role. So I want to know either a question about, okay, what's going to happen at a certain point in space over time, or what's going to happen at a specific snapshot in time of the spatial domain. Okay, you see? So that's sort of slicing, either slicing it here, right, and looking at a specific point in space, right, and looking over time, or slice it that way. Then I'm looking through space at a particular snapshot in time, okay? And I want you to be able to go through these equations. If I give you a certain f or a certain g, analyze these integrals. And there's usually some analysis component where you have to pick through those integrals or pick through the f part right here, these wave solutions from the displacement, in order to find out what the answer is. Okay? So people who draw pictures and are just very systematic about it do really well. I think if you I think that's the best way to go through these things. So it's going to have a qualitative component. Okay. So any questions on these? Did I hear some other examples? Yeah, where are they? Okay, suppose f is non-zero initial condition. What we have here is f of x is equal to 1 on x, okay, and 0 elsewhere. Okay. So find g of x such that u is equal to 0 on this interval after finite time t. That is, okay, so okay. So there's actually many such g's that will do this. I just want you to find one of them. Okay, so I guess the first question then is, what does we have the 1/2 f of x minus or plus ct plus f of x minus ct. Okay, And then we have this other thing here that we want to figure out, right? And what I want to do is have this thing cancel out this to make it 0 on a specific time interval, right? So this is an integral in space, right? So we want to find that. So what we want basically is that when this wave goes, that it just disappears forever after a certain amount of time. So what are we going to do? What's the solution look like here? We have to find out what that one looks like. So it starts off like this, right? And then after a certain amount of time, so this 1 here, right, this is going to be 1/2. There we go. It looks like that, right? All right, but so it appears as though this, I mean, there's already an interval where it's 0 here, right? The question is, where are the trailing edges of this function? So where's the trailing edges of these functions? So I want to know what is this point x of t? I'm going to call that x minus of t. This is x plus of t, right? What are those trailing edges of that wavefront there? X plus of t is going to be what? Has to be a function of time, right? So there's going to be a ct, right? Minus 1, right? Has to be, right? Because we start at minus 1 at time 0, and it's going to be going this way, right? And then x minus t is equal to c minus ct plus 1, right? Right. So at the beginning, both of these will be interacting, right? So we won't really see them. But they'll show up after a certain amount of time once t is greater than 1 over c, right? But you see here how this is going slower? See, we made this go, so we not c over t over 2, right? So how fast is that going? Does that seem to be, does this go, where is this interval going as time goes forward?
As time expands.
It's getting smaller and smaller and smaller, right? So it's 0. So I conclude then that g of x can be just 0. Because after a certain amount of time, for t, I'll just say greater than, let's see, 1 over c, I should do it. Yeah. So what does my solution say? Oh, wait, c over 2 times, okay, that's right. We need, this t needs to be up here. That's right. I read it wrong. There we go, that's better. This is still true, but this is going, if this went this unit in distance, right, this has gone half that. Half that, give or take a unit, right, a unit of time. So I think g equal to 0 should do it, right? Yeah. So the idea here isn't to find, a crazy G or anything. The idea is to go through the thinking of it. Can you explain to me what's happening to the system, and can you interpret the meaning of these statements, and give me a rationale for what's happening on these intervals? So I think the issue is usually, if you have a good intuition of these things, if you can read the mathematics and tell me what it's saying, and craft an argument about it, that's what I'm looking for. Okay, so a lot of people look at these intervals and go, and they just go, I don't know, I just give up. Okay, but obviously people are going to want you to be able to look at this and start picking through it. This is what we want to start getting our fingers into and understanding what this means and how it works in practice. And the only way to do it is to just start picking your way through it. Okay, so it's definitely a challenge. I think people always have a challenge.
When you said that it goes this distance and then you said another part goes half, are you saying the full? I was confused by that statement.
So here, this is your I of t.
Okay.
It keeps getting bigger and bigger and bigger, but it's like half the speed as your waves are.
Oh, okay.
Yeah. So at some point, once these things get farther, so at first they're crossing each other, right? So after a certain amount of time, they're still here, right? You're going to get a solution like this. And clearly, your I is going to be still, in that interval, you're just going to have non-zero stuff.
Mm-hmm.
But once these waves get farther enough out, right? Once they actually don't cross each other anymore, they'll take off and eventually they'll accelerate. They won't accelerate, but they'll be far enough apart that the middle will be zero here. Okay? In which case, say after some amount of time, so I wouldn't say for 1 over c, but for a time somewhere after that, eventually this interval will be free of any non-zero component.
And are the waves perpetually expanding in length and they're perpetually reducing in height, right?
They're always staying the same height. They're always
okay.
1/2. And this is the idea going back to the energy. You start by displacing this thing, and you let it go. Half the energy goes that way, and the other half goes that way.
Okay.
Yeah. But you never lose any energy. There's no friction in the system. So again, there's two components. There's this thing here, and that involves asking, does the domain of integration intersect with something interesting that's happening with G? Right? And that's all the questions related to this boil down to that mathematical query. Okay? And for the displacement component here, it's always about looking at these, a wave going to the left, a wave going to the right, and as they pull apart, the idea, what's happening? How can I describe that motion, where it goes, and being able to analyze that? So you're answering questions about the distance traveled over space, or over a certain time, say, and back and forth from there. So, any other questions on this? Hopefully this, yeah.
So for this problem, when it's like find the initial velocity that makes wave equation 0.
Mm-hmm.
So all we have to do is be able to show that we understand it correctly, and then knowing that we can just say g of x is 0.
Yeah.
We just have to show it that we.
So g of x equal to 0 is consistent with that statement. Yeah. So, and so the only way one can answer that, is to pick through the answer and say, okay, that seems to be satisfied for every when g is 0. That being able to infer that means you understand the left and right going wave solutions, how they eventually go apart and leave you with 0 in the middle. Okay, right here. So,
does the height ever change? Because on your top graph it shows 1 for your y, but then on the bottom graph it says 1/2.
So for t less than 1 over c, right?
Yeah.
You're gonna get the two half waves will sum to make a whole. So they'll look kind of like like a little stair step thing, right?
Sweet.
So Hubert can jump down it and stuff. Okay. So So it'll go like that, and eventually, and that's because these two interact. But then at t equals 1 over c, what you're going to get is the two half waves will be abutted to each other, like two bricks. Okay? And then for every time after that, they'll separate, right? Yeah. Okay. So at this point, the I interval would be, or where would it be? It'd be a half c, whatever that is. And your I would be here. But eventually, this thing is going to grow slower, while these two are going to grow twice as fast. So eventually, they'll clear out. Yeah.
So how would you find the time when somebody sort of passed that spatial boundary?
We could find it, yeah. So we have to find. So here are those edges, right? And I have to simply set. So that's x plus. And I have to set that equal to whatever the 1 over 2c, right, times t. Okay, and then I have to find the time where those intersect. So that's ct minus 1 is equal to 1 over 2ct. Oh, the c is in the numerator. Sorry, I keep doing that. There we go. All right, so we just have to solve for t, right? So I have a half ct over here and a whole ct over there. How many ct's do I have? Just the half ct, right? So the t star, so this is equal to that capital T, I should say, is going to be over c. That's when you're going to get the situation where I of t, here's I of t, that interval, will finally be completely zero, right? These waves have finally moved out of the way enough to not cover that zone in the middle there.
Can we get like a random form with that?
What's that?
Could we like get a random form?
A ramp one? I don't know what you mean by that, but we could do a one that does involve rampy things. You want me to do one right now?
No, yeah, I just saw like there ones that would go out like ramps.
Yeah. So if I have, we can go with the same one. So after that is this thing here. Make a G. Okay. Then you get rampy things. You get trapezoids. Alright, so we'll just say again f is equal to 0. I'll just say c is equal to 1/2.
This is really similar to Q.
Oh, okay, good. Alright, so we'll say c is equal to half, so I'm going to do this. And then we have g is Alright, so, yeah.
Sorry, so when you have f of x is equal to 0, that just blows out all of the position terms. Is that correct?
All of this is gone.
Yeah,
right
so
here.
it just knocks all that out, and all you're left is with the velocity term.
Yeah, so this is the solution here then, right? There's no f's anymore. There's none of that left and right hand stuff. All you have is this thing to deal with. Okay? So that's your solution. Now I want to get to it. So here I might ask you to break it down further, like I want to know what's happening at a particular point in space. So again, I'm standing at a particular point in space and I want, what's going to happen? What's going to hit me? At some point I'm going to get hit by this wave that's coming, right? So I want to know, and what's the nature of that wave? Is it going to be a giant wall? Because we've seen some that look just like, they're just like a wall that comes at you. In this particular case, it's going to be more like a ramp. It's going to kind of gradually go up, and then it'll level out after a while. So let's talk about that.
Where does C go in your limit?
I just said C was equal to 1/2, so I could cancel it out. Oh, yeah, so, there you go. There we go, that's better. Okay. I'm going to say C is equal to 1. And put the 1/2 out front. That's better. Okay. Okay, the unit speed wave, okay. Okay, so a lot of times when you see an x minus ct, that's what they call a moving frame. And so a lot of times they'll use moving frame coordinates. Sort of like if you want to x minus ct, x plus ct, they call moving frame coordinates. So if you're surfing, right, you're in a moving frame, right? The wave is stationary with you. You're traveling with the wave, right? So you're looking at the shape of the wave, even though it's moving, but it looks stationary from your perspective. So that would be an example of that. So other examples, if you're in something that's diffusing, but there's also advection, but you're moving the same speed as the advection, is as if there is no advection, right? All there is diffusion, because you're moving down the river with whatever's diffusing, right? So you're just going with the current, as it will, right? Those are the metaphors. All right, so let's talk about this one. So I'm going to break this down a little further. Maybe we'll say at x equals 10, what's going to happen? What's the profile look like? I want to know x is equal to 10. So then what I want you to do is draw draw and find u of 10 comma c. So I want to know in the time domain what happens when time equals 0 forward. All right. So I would start with my x equals 10. So this is the C domain, right? I started at C equals, so I put a 10 in there. Put a 10 there, right? And now I'm going to see there's a 10 minus t, also a 10 plus t. Right? But where at 0, so this is maybe I should draw this to scale. There we go, that's better. That's 1 and that's negative 1. Okay? So there's my domain of integration. For the time that I've drawn here, artistically at least, is this domain covering anything non-zero for the function t? Yeah. So it's when this domain of integration, when that edge of that domain hits that point, that's when we're going to get something coming out of it, right? So what is that time? I want to know when this thing right here gets to 1, right? 10 minus t is equal to 1. What is 10 minus t equal to 1 is it going to be? T equals 9. So that's the dividing point. So I'm going along. At 9, that's when something finally happens. Okay, so it's 0 all the way through that. So I can actually write that now. U of x 10 comma t is equal to 0 for t in the range 0 all the way to 9. Okay, now, what's going to happen after that? I'm going to pull this down again here. Right after that, I'm going to go like that. How much area is under the curve then? There. The area under the curve is just this little sliver right there, right? And it's going to keep increasing as my time goes, as this boundary of my integration domain keeps moving until it covers the whole thing. And at what time will it finally cover all of it? So at t is equal to 11, oops, 11. What is the area under the curve? What's the area under the curve? 2, right? Of course, we divide by 2, right? So what we know then is that for t, then after I go past that, right? What's the area under the curve after that?
The same.
It's the same, right? It's always the same, right? Because you're still covering this. You're just not getting any more area under the curve, right? So it's not 0. It's always going to be 2, right? But we're going to divide by 2 because we have a 1/2 there. So we say it's 1 for time greater than 11, and then it's all the way to infinity. Okay. So what's happening in the middle here, right? What's happening here? We see it. Yeah, it's growing linearly, right? The area under the curve is growing linearly. So at what slope? How much area do we get for 1 second? For the 9 to 10 seconds? 1, right? For every second we get 1 unit of area, right? Okay. But we're multiplying by 1/2, so we got 1/2 times t, right? Then we have to minus 9, right? Because we have to advance ourselves up, right? Does that work? And that's for t in the element of 9 all the way to 10, or 11. Okay, does that work? So here's my graph. There's my 11. When I get to 11, this becomes 11 minus 9 is divided by 2 is continuous. So again, this is in time, so that means if I'm sitting here at this point and I'm watching the string, I'm at x equals 10, I'm watching the string, I'm waiting for 9 seconds, and then it starts going up at a linear speed, and then it stops. And then it's that way, it's at 1 forever after. So that's the motion, it goes like this. So again, if you're doing anything involving waves, waves have finite propagation speeds. They don't instantaneously occur. They actually take time to get somewhere, right? So if you're doing modern physics, you do relativity. That's very critical. Everything's done in space-time. And if you're doing any kind of mechanical vibrations, a disturbance that happens at a point, it takes a while to propagate to get somewhere else. And that finite propagation time is all related to this kind of thinking. So that's what I want to get you used to doing. It's the PDE's class, and it involves 2 variables. Yeah.
So, in past physics classes, the C term was always dependent upon the medium. Mm-hmm. Is that correct? Here, we're just kind of choosing easy numbers to be able to kind of go through it.
So for this one, the medium depended on C was C squared was rho over, it's the other way around. It's the tension on the string over the mass density. Yeah. So in electromagnetism, it's of course the speed of light, and the Maxwell's equations have wave solutions. When you reduce it down, it becomes a wave equation. Although the waves there propagate not just in a one-dimensional thing, but also they propagate outward in 3-dimensional space, but they have a linear speed. So as you've seen, if you drop the pebble in a pond or in a lake, right, it propagates out. The linear speed, the radius of the disturbance grows linearly, but the energy gets spread over a thinner and thinner shell, right, as it goes forward. So neat stuff. But how to tackle all that requires understanding space-time, and that the time it takes to get from one point in space to another point in space getting used to solving those types of equations. That's what we want to do here. Other questions?
Can we do a kernel problem?
Yeah. Oh, perfect. Well, we can do a very generic one. Or should we do a specific one? Earth function? Sure. Okay, so Earth function show we have, well, let's just do one that's,
If you want, we could just go over the practice exam one. Read,
which one is that one?
15,
15.
I believe.
Okay, that is from A to A or something like that. Oh, okay.
Is that 15?
Okay, yeah, okay. All that after that. So this has what's the total amount of stuff here at time 0?
1 over A, yeah. Oh, that's X equals 0.
So think of this as mass density, right? So we integrate to get the total mass. Right?
Mm-hmm.
So what we have is 1, right? So this is 1 over A, but it's from 0 all the way to A. So the area under curve is equal to 1, always.
Okay.
For all A. Okay? So it's a finite amount of stuff, how thin I spread it, right? So it's a unit amount of stuff, but I spread it either wide or really skinny, right? So of course, if I take A to 0, what's going to happen? We're going to approach the delta function, all right? Of a really brief pulse of stuff, a brief spatial extent of stuff. Okay, so let's do this. We have U is equal to U times X. Do I give a diffusion constant for here? Do I just say K equals 1, right? So that's just 1. So we can cut right to the chase. You don't have to, if you want to do the Fourier transform, but the solution is always going to be the form U of X times T is equal to the heat kernel involved with F. And that's going to be X. T is a parameter in the heat kernel, right? So what's the heat kernel? It's going to be 1 over 2 pi. What's it going to be here?
4KT.
Okay, it's 1 for T times, and this is on your equation sheet on the front of the exam, you get all of this, right? They made it so these 2 pi's always cancel. Okay, so there you go.
Yeah, sorry. The F term, F squiggly, I can't even say C.
C?
what is that? Is
It's
that
a variable of integration.
with respect to our f of x? Or is this, because you got your f of x term up above.
So when I write, so I'll put h involved with p, two functions, right? We've defined it as so again, C is, I use a jarring kind of C is a Greek letter that I use it so it's not doesn't distract anyone, so everyone realizes it's a variable of integration. Yeah, so I always use that one as convention. A lot of people use it for variables of integration. It's again because it can't be confused with anything else, right?
Sorry, this is like an abstract with all things. So, do you actually solve for it? Or does it just kind of like kick around as you move through it?
So this, remember when you're integrating over this, the C goes away because it's integrated over, right? It's sort of like, I think, coming back to more of a calculus thing, right? If I have A to X, that's f of C, B, C, right? If I have this sort of thing, right? Call that little f of x, right? It's not a function of Cassie. Cassie is the variable of integration, right? So what we're saying is there's some capital F here, and there's A, and there's X. And X is variable, right? It can move along, right? It can move along this axis here, right? C is integrating through all the way to S. So that'd be another example of how a dummy variable shows up in the integration. Yeah. So convolutions, of course, play a major role in any kind of signal processing problem. So mechatronics, you're going to do convolutions and stuff like that. Anything involving signal processing. Convolutions. A lot of times the output from any kind of mechanical system involving actuators, servos, things like that, if that's your input signal, this represents basically, the output signal comes through this convolution over some sort of kernel function that represents basically how responsive, say, the servo is to inputs, right? You can tell a servo you want it to move at 1,000 hertz, but it won't do it. That's the idea, and the kernel represents the fact that that's not always entirely possible. Okay, so convolutions, we've seen them in Math 2250. We've seen them here again. They keep showing up. Okay, so here's our function we want to solve. So in this case, Cassie, F, what is F now? It's only over the domain 0 to A, right? So the only place where this thing is non-zero is over a finite domain. So I can replace this by the 1 over A, I can actually move it right out front, right? There we go. So, for these sort of problems, I'm always going to say, I'll make it very clear, for these sort of problems, I want you to express your final answer as an earth function. Okay, so earth functions, again, are one of those functions that shows up all over the place. They gave it a name. It was so common. So how do you define an earth function? Should be on the equation sheet right on the front here. again, that dummy variable of integration shows up, right? Zero to x e to the negative, and I said s squared over e to the negative s squared ds, right? So s now is that dummy variable of the equation. I could put c there if I wanted. Just, oops. Okay. So I want everything in that form. So this function, you can find it on your scientific calculators, you can find it in MATLAB, you can find it in all the scientific computational libraries, and it's numerically efficient. A lot of the work to make sure it's accurate is done for you. It's used often in statistics because the ERF function is a Gaussian, it's an integral of a Gaussian function, right? You cannot find an antiderivative for this function, for the integrand here, right? Only can be computed numerically, but it's such a critical function for doing anything in probability and also in diffusion that it shows up. Okay. All right, so there's your ERF function, and now I have this. And I want to work on this thing until it starts looking like an ERF function, okay? So, again, if I write it down in this form, then I'd have to actually compute this integral, which would be hard, okay? By getting into an ERF function format, then I just punch it in my calculator, out comes the numbers, right? So, that's why we want to do that. So what we see there is that we have, first of all, the square root of 4 pi t, that's a constant with respect to the integration variable, right? So, then we have all of this stuff, and I'm going to write it a little bit different. So, I'm looking at the ERF function, I see that there's this s, right? Quantity squared. So now I know, so here I have a d to c. So what I need to do now, to make it look more like an ERF function, is I need to do a change of variables to simplify that integrand, okay? So I'll say let s equal Alright, there we go. So again, I need to swap out the d to c for something ds. Right? Anywhere I see one of those, I can put one of those in its place. Now I need to plug in 0, right? So I plug in 0 for C and I get, and then I plug in A, I get X minus A for C, right? And now I have an E to the negative S squared ds, right?
Did you lose a negative?
Oh, I need a negative. There we go. Okay, so I'm getting close. So I see my limits of integration are pretty wonky, but those, we know that input to the ERF function is this x. You stick it in the limit of integration. Lots of functions are defined in terms of derivatives, in terms of integrals, where the limit of integration is where the variable is, where the input variable is. Here we see two of them, both top and bottom, but there's a rule for integration, right? I can always break up my domain in two pieces. One thing I'm going to do is, I see this line with a 2 there. So if I put a 2 here and 2 there, I'm good, right? So now I have negative 1 over 2a And then I have I can say 0 all the way to x minus a 2 over pi, root pi, x minus a to the 4t, over 4 root 4t, e to the negative x squared dx. And then I have also what? Minus 0 to, well, let's be more, I'm going to be really precise here. Okay.
Where did those 2 come from? Is that from the Earth function? The 2 over square root pi?
I needed 2 over square root of pi here as well. So that came just out of, this came out of here, all this stuff. It came from the change of variables that ended up showing up. I mean, they defined the Earth function very conveniently to work very well with the heat kernel. And the Earth function literally is, so if you were to, so if I'm going to take this to infinity, what's the value? Is it 1? What it literally means is it's the area under the curve from x to negative x, the Gaussian function. Yeah, but we're changing it by 2 because it's symmetric about 0. Yeah. So it's looking at the area under the curve at 0. That's what the Earth function does. So again, it's very important in probability theory. So anytime you do statistics, Earth functions show up a lot. All right, we're almost there. Now we flip the sign, and I have that negative there, so I'm going to distribute that in. All right, so, and now I'm going to flip the sign again. Put this up there. Okay, so there we go. So this is Earth of x minus a over 4 minus Earth plus Earth x over 4t. Or over root 4t, sorry. Okay, so the answer is 1 over 2a So if the area under the curve is this sort of Gaussian thing like this, it has a plot. Of course, it's 0 there. It has a plot that looks like this. That's the plot of the Earth function as you go forward in x. Right? We see here, we go forward in x, we see that there's this 1 over root 4t in the denominator. That tends to undercut the x, right? So I can move forward in space, also move forward in time, and actually be a fixed value here. The idea that you always get an x to the first power and a t to the 1/2 power, that's a very common in any kind of diffusion type system. We call that what happens is basically as you advance the unit in time, you go, space is squared, effectively. And it says that deviations from 0 typically are on the order of s squared for every unit of time. Okay. So this sort of thing is gonna, it's gonna look like this. Starts here's negative 0 to a, right? So the time going forward, you're gonna get like that, right? Really big. It starts looking like this. Because as time gets bigger, right? In order to get this, this function is sort of like this, right? So here I am, x at 1, But when time gets bigger, it's effectively moving me back, right? And I have to go further forward in space to match that, right? And that's why it goes like that. So being able to change the variables like this to get things in Earth functions, they've done a few of these problems now. There's one more here today. So, question?
I would have a hard time, like, just guessing that I should use the kernel function kind of thing. Are you going to hint on the test that, like, put your answer in error form that way?
Yeah, so I say use the convolution formula. So, I mean, this is true for any, the solution to the heat equation on the real line. So it's on here, on the front sheet here. Where is it? Here it is, the heat kernel. Okay, that's the heat kernel. And the solution to the heat equation that's always a solution in the equation. Again, the convolution shows up over and over again as solutions to these equations. So again, if you've done my 3160 class, you've seen this on Tuesdays and Thursdays, and we keep doing this. And you did it in 21252. Convolutions show up everywhere. Okay, so this is the definition of the solution to the heat equation on the real line. So at where u of x comma 0 is equal to x. That's your initial concentration or initial temperature, depending on diffusion or heat. Okay, so stay a little later if you guys want me to. Okay. Should we do a Fourier transform question?
Yeah.
Should we do one of these ones on the list? Let's do, we can do both in parallel. Did I already do these ones? I feel like I've done them. So there's u, p, p equal to negative u. There's also u, p equal to negative u. We did this in class. Are you okay with them? Did I do a different one?
Yes.
Okay. All right. Okay, it's the first order in time, so of course we have u, x, and 0 equals x. So this is the convection equation. So first you get capital U is equal to, what do we do with spatial derivatives? What happens? This is a differential equation we can solve. Right? We're just solving this differential equation where this is that constant. We're seeing a ut is proportional to something with u. We just solve it like that. I think the key here is, yes, there's an imaginary number there, but just treat it like any other constant. All right. So this is actually a function of omega, and it has to be equal to the Fourier transform of little f, right? whatever that is. Right. So what we get then is alright. So here we see this e to the negative omega t. What we're looking at here is we need to go again to our Fourier transform tables and recognize the following fact. The shift theorem. Anytime you see something like this with a single power of omega up there in an exponential, you should think shift theorem. Okay. So let's say this I t omega. So the shift theorem states the following. Should be on here. The shift I don't need. X plus A is equal to whatever the Fourier transform of f non-shifted is, e to the negative I a omega. So what is A in this case?
T.
T. Alright, so now we need to take the inverse Fourier transform of big U, and that gives us little u. And we see this has to be f of x plus or minus t.
Minus T. Plus T.
Alright, so you have your initial whatever condition for your EE. What's going to happen in time? Right. It's just going to translate, right? Is it going to translate left or right? So as time goes forward. Good point. You never know, right? We're not doing thermodynamics. We don't know about the arrow of time. Time is reversible. Okay, so it's going to go to the left at unit speed.
Why is it plus t?
It just happens to be how it worked out. Okay? Because we started with a negative ux up there. Right, so this is an EE here, so this, you can think of this, again, now let's go back to, page 1 of your exam, which is all this stuff related to flux and all this stuff, right? What is this PE saying? Well, we can unwrap this, right? Alright, so what's the flux?
U.
I feel like I screwed a sign up here. I did. There we go.
How were we able to say A was equal to T? I just missed that.
Because we saw this right here.
Oh.
So we saw capital F multiplied by this exponential.
Okay.
First power there. We're scanning for things that look like the shift theorem.
Okay.
So we're actually moving the other direction. So where was my error? it showed up. So what's the Fourier transform of a derivative?
Is it negative I omega?
Yeah, where is my mistake? So that's the Fourier transform, correct? Yeah, I think my identity is messed up. I forgot. I'm missing a sign on it. This goes to 0, by definition. Got my minus sign. So I'm gonna have to fix that for I will fix that on your equation sheet. So yeah. Sorry about that.
Sorry, what part exactly was it?
The derivative identity should be the Fourier transform of the derivative needs to be negative I omega capital F. So what happens is when I take the Fourier transform of the negative derivative, I get a positive I omega because the negative and the negative cancel. So I'm tolerant to sign errors, of course. We all make them. It all happens. It's the most common error. Okay. So this is an advection style equation. So you see the flux is U, so the flux is rightward in proportion to how much? Right? Because U, there's that much there, that's how much is moving, right? Right? So if there's less there, there's less moving. And the idea here is that there's some velocity usually involved. You have a unit velocity, and that's how fast stuff is moving. But talking about flux is how much per unit time. So if there's a high concentration moving through space, then of course there's more flux. Okay, so flux should be proportional. So for advection, flux is proportional to the speed, which in this case is just 1 times the amount that's there. Okay. So, a lot of this can be done without actually computing a Fourier transform, via integration. It can be all done symbolically. So, I may have other problems, of course, that say, okay, take the Fourier transform of this function, analyze it. What did I ask you to analyze? I had a couple of these problems on the exam, so I just want to prompt you guys here. So what's the other thing that F tells us? What does capital F tell us? Energy spectrum, right? So computed energy spectral density, right? So what's the ESD?
F omega times video.
F times the conjugate. Alright, so 7:30 tomorrow. We'll be here bright and early. Okay.
Fun.
You got any questions? They're going to be on the